Hello, this is Josiah Winslow recording for his Data Structures and Programming course at MATC for instructor Mark Cribb. Well, today is the due date of my final project, and I have to say I'm a little bit more proud of this than usual. So, the requirements for this final project are very, very broad, but I was able to latch on to the extra credit line down here, where for up to 10% extra credit, we can use data structures to implement a simple dictionary that allows the user to search for a word and offers "Did you mean?" help if no word is found. And I thought this was a simple enough question, right? I mean, what sort of algorithms exist out there for figuring out how close a word is to another word? And I came across this notion of Levenshtein distance, which is basically edit distance, where insertion, deletion, and substitution are considered primitive operations. There's also something called Damerel-Levenshtein distance, which also includes transposition, of two adjacent characters, but I decided not to use it for my dictionary example. And looking at these bits of pseudocode for implementing different algorithms to calculate the Levenshtein distance, I came across this one that, given two strings of length m and n respectively, sorry, I can't talk. This runs in O of mn time and O of n space. And I thought this was very, very good and efficient enough probably to use on the entire dictionary. But when I tried doing a naive implementation of doing this function to every string in a dictionary in like a giant list, it took like multiple seconds to do it, which is multiple seconds too many. So I tried to look up ways I could do it more efficiently, like for instance with Levenshtein automata. Trouble is, I don't understand Levenshtein automata in the slightest. And when I tried to look up ways that people have implemented them before, all of the simple implementations were not very good, and all of the good ones were not very simple. So no luck there. But I did see this sentence right here in the Wikipedia article for it, which helped me develop my idea. If the dictionary is stored in compressed form as a tree, that's a prefix tree, the time for this algorithm of figuring out which words are within a certain distance of a given word is proportional to the number of nodes in the tree, significantly faster than using dynamic programming to compute the Levenshtein distance separately for each dictionary word. Now, again, I could not apply this to Levenshtein automata because I didn't understand them, but I could work with trees. I could use them to perhaps speed up this algorithm right here by combining traversal through all the nodes of a tree with the inner loop of this Levenshtein distance function. That way, for every prefix of every word in the dictionary, I only have to calculate up to that row of the matrix once. And by the way, a tree or a prefix tree, if you don't want to get confused, is a tree where each branch, each edge, represents a letter, usually it's a letter, and every word with a certain prefix is stored as some node in this tree where you take some path down from the root. For example, all the words in this tree right here. So this node is the beginning of the word. This node has every word that starts with T. This node has every word that starts with TE, and all of them are some level of children of this. And it's very efficient to store all of the words in a dictionary if all of them, or a lot of them, share a common prefix. And also for searching for a value in a tree. it is also very efficient. It is proportional to the length of the key which you're trying to search for. And so is insertion and deletion. And I thought, hey, this might be a really, really good thing to apply to this algorithm, as I think I did an overview of before. So, let's get into how I implemented the tree. So, each tree, I'm treating each instance of this class tree as a node in the tree. And what parameters does it have? It has self.data, which is some sort of data that is stored with the node if it is a word. IsWord, which is a Boolean, determining whether or not this node is actually the end of a word. Edges, which is a dictionary with string keys and tree values, which store connections to all the children. And also, as a little bit of an implementation detail, for keeping the dictionary of edges in sorted order, I use this is sorted right here. And down here in the private methods, I have something called sort edges, where I call this, by the way, on every node if I'm doing something like iterating through all the nodes. And what it does is, if this is marked as not sorted, rebuild the edges dictionary by sorting its items and packing it back into a dictionary, and then setting is sorted to true. And this way, every time it goes through the string, goes through all of the strings in the tree, rather, it goes through them in alphabetical order, or reverse alphabetical order, as the case may be. And the complexity of this operation of iterating through in reverse, instead of running in that amount of time, it runs in amortized time, which is basically the average among all calls of that function, or all runs of that function. It's a different sense of average than is usually meant in like an average case analysis. And now let's get into my main function, or my main program. So, I actually use a few different modules to help me with various things. For example, this gdown module helps me download from Google Drive, because apparently it's not as simple as making an HTTP request like last time. I also use WordFreak, or word frequency, which is a module that helps me get the frequency of a word in a certain language, in this case English. And I also use sorted key list, which is a data type from sorted containers. Now, originally I was going to use my binary search trees, and in fact I did a little bit of a modification to my binary search trees specifically for this assignment, where I added a size parameter to all the nodes, and this made my get item function take up a lot more lines, but it is way more efficient in terms of time. Instead of being O of n, it's O of log of n. But the sorted key list right here was much faster for, well, I wouldn't say much, but it was faster for the application I was using it for. Is there anything else I'm forgetting? Oh yeah, I'm using the text wrap module again. So, here we have the Scrabble scores for every tile or every letter. and a function right here to calculate the Scrabble score. Because guess what? We are using Scrabble words. So this is a copy of the dictionary that I'm using. Again, I'm getting it from Google Drive, and I'm not uploading it to GitHub, but the code that I have will download it for you. And these have all of the words that are legal in Scrabble as of 2019, and then a tab, and then the definition of the word, which is a very, very simple format to parse. And so let's just get past this search tree function. This basically, the guts of this is a sort of recursive tree iteration combined with a Levenshtein distance search function. And every time I get a node that is a word where the cost is less than or equal to the maximum acceptable cost, I add it to the results list. And the results list is, ta-da, a sorted key list. So anyways, here is where I download the Collins Scrabble words with Gdown, and I use cache download to make it so that if you already have the file on your computer, it will not download it again. And then I create the tree, and after I open the path of the dictionary file, first I skip the first two lines, which is just a header and then a blank line. And then I split the line into its word and definition. I convert the word to lowercase. And then I index into my tree to add an entry at that depth into the tree with all the paths corresponding to the characters in the word. And then I print the length of the tree, which I've defined recursively right here. And by the way, this will also sort all of the edges of the, each node of the tree, which I haven't had to take advantage of yet. I haven't. There's no real reason for me to do this other than I just want to see, how many words that I've been able to store. And I have a few functions that this final project does. One of them is looking up a word. So I have a search term entry function called input word. And it searches for, well, first off, it checks if the search term is in the words tree. And if it is, it takes that entry and then prints it out. And then each entry stores a definition and a Scrabble score. And both of those are output. However, it also does this function right here, which was the tree traversal combined with Levenshtein distance calculator. And I have it searching for 100 results, and I have it searching up to the default max cost of the length of the word divided by 2, but rounded up. And here, at the suggestion of Mr. Crib, when I showed him an alpha version, I think it was a few months ago, it might have been, or a month ago, I have it, in addition to sorting by Levenshtein distance, I have it sorting descending by word frequency, and within those, the next key it tries to search by is all the absolute differences of each of the code points, which is my way of approximating how close they'd be in a dictionary. Your search term and whatever word we're trying to search for. And here I use perf counter ns, which is an accurate to the nanosecond timer to check, how long something took. And then I convert that to a string, and then I print out the search results and the time elapsed as the formatted string. By the way, again, I am really surprised that this is a standard library module, text wrap, because I wrap all of them in lines of a certain length. I also have 3 more functions. One of them is find words starting with prefix, where I use the query function of my tree, and it's just iterates through every one of the nodes that starts with a certain prefix. And I use this walk prefix method. I use this a lot, which is why I delegated it to its own method, where I take every character within a certain prefix, and then I walk through all the edges till I get to the proper node. And then the query function just uses the iteration and yields all the words that start with that prefix. And then finally, the 2 simplest functions, add word to dictionary. And here I also have a check if the word already exists in the dictionary. It asks you whether or not you want to overwrite it. And if you do, then great. It asks you to input a definition. And then it sets that entry in the tree to your new entry with the Scrabble score of the word. And here we have remove word from dictionary, which this is even simpler to do. I just have to del words word. That's great. And then standard main loop, which has all of these functions right here, and it asks you to choose one, and then it does it. All right. So let's actually get to running this. So it'll take a sec to create the tree, and then once it's done, it usually doesn't take as long as it just did, but here we have all 5 of our functions. Well, 4 of them, and then the 5th one is exiting. First, let's look up a certain word. Let's try to look up computer. All right, so we entered a word that is in the dictionary, computer. It has a Scrabble score of 14, and it has the definition, a machine that computes automatically, which is great. But perhaps you meant computers, commuter, compute, computed, computes, compter, compete, and so on and so forth. And these are all some of the closest words in the dictionary that, the closest words to computer that exist in the dictionary. And would you look at that? It took 929 milliseconds to find all of these words. That is 0.929 seconds. So I'd say that's pretty good. And what if I wanted to look up oranges, but I spelled it wrong? You entered oranges. Oh, did you mean oranges with an A instead of an I? Or maybe you meant fringes, cringes, orange, brings, rings, bridges, ranges. And you can kind of see how they're close to the search query that we want. And this time it actually took even faster to find all of these examples. 368 milliseconds. That's 2.368 seconds. And what I've found is I've had a lot of fun testing this out, and I like testing it out on just random gibberish just to see what it does. So this doesn't really make sense. So it took like 2.366 seconds to find these examples of close words. But apparently the closest word to rubwo is rubber. It could have also been rubbed, rubies, rubbers, rubbery, subwoofer, rubidium, and so on and so forth. And if we actually look up one of these, like maybe rubidium, then it'll find the Scrabble score of it and the definition. And it'll also calculate the words that are close to it. Alright, now let's test out find all words starting with. So, maybe I want to know how many words start with R-U-B. And would you look at that? It found 161 results for words that start with R-U-B. And this was really quick to access because it just involves going to R, U, and B as paths in the tree, and then iterating through all of the words under that node. So we get words like rub, rubaboo, rubaboos, rubase, rubases, rubai, rubiat, and so on. Actually, what's rubaboo mean? A type of soup. That's interesting. And what if I wanted to add a word that I thought should be in the dictionary? Like, for example, if I look up Josiah, that isn't a word in the dictionary. But maybe it should be. So, I'm going to add it. So, enter word, Josiah, enter definition, the one who made this final project. And it's a noun. I didn't have to format it like that, but all of the other definitions are like that, so I thought I would. And so now if I look up Josiah, here I get, apparently Josiah has a Scrabble score of 16, and this is the definition. And perhaps I meant, this, that, and the other thing. And let's say I look up Joseph, then Josiah should show up as a word that is close to it. You see, it does. It thinks Josiah is a word now because I added it in. And now let's say I've had enough and I want to delete it. Well, I'm going to delete Josiah. Josiah removed from dictionary. Okay, so now if I look it up, it doesn't think it's a word. And if I look up a word that's close to it, it doesn't show up anywhere in here in the results. And apparently Joseph, by the way, Scrabble does not allow you to use proper nouns for words, but it does allow some words that look like proper nouns in senses that are not proper nouns. For example, Joseph means a caped overcoat worn by women in the 18th century for riding. And there's also a noun form that ends in S. So that's kind of interesting, I would say. Let's look up some more gibberish, and then I'll quit out of this. So, Whirlpool. Did you mean Europop? That's a Scrabble word. Wow. That took me by surprise. Alright. Desai Hansu. Did you mean diamonds? Draghounds, diaphones, dicons, diamonds, diamonies, seconds. Seugostner. Did you mean slughorn? This is all lovely. You can probably see why I had, like, so much fun just, like, entering gibberish into here. And apparently this word right here is so far from anything in the dictionary that within the specifications that I specified, there are only 2 words that are close enough. Did you mean sinfonia or algolagnia? Let's look these up. Sinfonia. Italian, a symphony orchestra. Okay? And algolagnia. A perversion. Okay. Now's as good a time as any to exit. So, I hope you enjoyed it as much as I did, and I certainly enjoyed using a tree in this unique way to search for the closest word in a dictionary of words. It was actually a very fun and fulfilling exercise. So yeah, take care, Mr. Crib, and hopefully I'll be able to be in touch with you even after the school year is over.